audible, right? I'm not using the headphone. Yeah. So, well, this will be your last lecture on logical effort. So, you might remember in the last class, we were talking about optimizing the buffer size or inverter size, right? I gave you one problem, I think, which I can remember. I gave you 2 femtofarad load at the input side and 180 femtofarad outside output side, right? I also gave you mu raised to mu p, how much? 2 raised to 1. The question was, what should be the optimal size of this buffer? Means you are not concerned about whether you are, if this is x, you are getting x bar or you are getting x. Either you are getting a true form of the output or you are getting a complementary form of output. Let's say you are not worried about it. You are okay with both output here. You are okay with x as well as x bar. Then the question was, what should be the size of this chain? That how many inverters you can put it here, because you know that if you have one inverter and another inverter, then this is x bar, then again it happens to be x. And again, if you put one more inverter, it is again x bar. So logic function is not changing. So the question was, based upon this particular one, is it good to have only one inverter, or you can have 2 inverter, or you can have 3 inverter, or you can have 4 inverter or 5 inverter? Then I think you did some computation of the delay and everything. You find it out for n equal to 4. If you are connecting the 4 number of inverters, you are getting the least amount of delay. Yes or no? This is what you did last time, last class, correct?
Yes, sir.
Now question is basically doing it from one step to another step, like from n equal to 1 to n equal to 2, n equal to 3. You are doing every time you are computing it. Is there a direct method by which you do know that what will be the optimal size of a chain? For example, if I simply change this problem statement somewhere like this, let's say I do have an AND gate, and then do I have an OR gate, 3 input, and this is my input capacitance 2 pic of or 2 femtofarad, and this is the node, this is the some node, right? And this is the output node y, and you have 180 femtofarad load. So if I say optimize this path for minimum delay, what you will be doing? If I say optimize this path for the minimum delay, you know right now what is the n? N is 2, correct or not? There are 2 number of stages, right?
Yes, sir.
Optimal delay is how much? N into the f to power 1 by n plus summation of the parasitic delay, 2 unit here and 3 unit here. How much? 5. Correct? 2 unit parasitic delay here, 5 unit, 3 unit here. That will be the delay and the unit will be tau. Correct or not? Correct or not?
Yes, sir.
And in order to obtain this particular amount of the delay, you need to make sure that G1 H1 of this stage is equal to G2 S2 of this stage, which is equal to f to the power 1 by 2. Yes or no? This is what you will do. Correct?
Yes, sir.
And based upon that, you will find out the capacitances here. What is the capacitance here? What is the capacitance here? And based upon that, you will be able to size what should be the WYR of this transistor, what should be the WYR of this transistor. So that was the method we adopted. But do you think this answer is optimal? Still, is there any scope of improvement? Means given the size of chain, if the size of chain is supposed to be only two, only two gates are here, right? If the size of the chain, if you cannot change, then definitely it is optimal. But if I give you the liberty and I say at this particular point, it doesn't matter to me whether I'm getting y or whether I'm getting y bar, then can you add couple of more inverters here?
Yes, sir.
You can, because you know that if you, even if you are adding more number of inverter, it is not changing your capital F, it is still unchanged. Correct? Correct?
Yes, sir.
But if you know, you are not right now sure, you know that if you use it and if you believe it has to be like there are only two stages and you are optimizing it, then in that particular process you will see that delay is that much only, 2 into f to the power 1 by 2 plus 5, that much amount of tau is the delay. But there could be like possibility, if you increase the size of the chain, the delay can reduce further. The delay can reduce further. That is what we need to identify, what should be the optimal size of a chain. Now we are looking of optimal size of the chain. Getting? So here come one way of doing it. I'm directly taking the figure. It will help me. Look, can you see? Let's say there are n1 logic gates already available. Means let's say you have this circuit already available here, one inverter, then an OR gate, then maybe another 3 input NAND gate. Let's say this was your original chain. This was the input and this was the C out, right? And if you, and let's say these are how many number of stages are there? Let's say n1 number of stages are already present. This is what I mean. But I know that I can optimize it individually. I have optimized it. I can optimize it properly. But I'm not very sure whether this will give me the least possible delay, because I know that even if I add up additional inverters, it may result in better results. So what I'm trying to see that I do have n1 number of logic stages here, right? I'm trying to add n minus 1 extra inverter before the output. Can you see? So what will be the effective size of this chain now?
N stages.
N. You're getting? N1 was your original circuit, which is having original number of transistors was N1. I'm adding N minus N1 extra inverter. So my size of the chain becomes capital N, correct? Correct?
Yes, sir.
I also know that the path effort for N1 number of transistor and for capital N number of transistors still is same, and that is equal to F. Right? Right?
Yes, sir.
If it is so, what will be the delay now? The least possible delay will be D equals, right now you still don't know what is the N. Question is what is the N, or what is the N minus 1? What should be, how many number of extra inverter I should add it up? Right now I don't know. Let's say I have find it out the what should be my optimal size of N. Then again I do the same method of logical effort. Then I will find it out. The delay will be N into F to the power 1 by N plus summation net parasitic delay of these N1 logic blocks, I equal to 1 to N1 plus these extra inverters. How many extra inverters you have added up? Let's say P inverter is the parasitic delay of an inverter. Isn't this is going to be my expression of the delay now?
Yes, sir.
So I want to find out what should be optimal value of N. What should I do now? What is the way? I can do del D by del N and put it equal to 0. Will this give me the optimal value of N, or yes or no?
Yes.
Yes, sir.
So can you do it now? I'm putting it up to you. Put del D over del N equal to 0, and this will give you the least amount of, this will give you the N value of N. And once you have done, let me know.
So why are we doing this?
See, I know that if there are N1 stages blocks, I am again coming back to the example. I show you this example, right? If I say my circuit is having only two stages, right? Directly then 180 femtofarad load and 2 femtofarad. I can optimize it. How I am going to optimize it? I'm putting G1 H1 equal to G2 S2 equal to f to the power 1 by 2, f to the power 1 by n. It will give you the delay D. This delay D is minimum provided that you cannot change the size number of the logic gates within a chain. But you also know so far from our analysis that even if you add up extra inverter, it is not going to change your F, right or not?
Yes, sir.
You might do remember that couple of exercise which we did yesterday or the class before yesterday, we find it out that though you can optimize a single inverter for, let's say, the same application, 180 femtofarad and 2 femtofarad, and the least amount of the delay will be, let's say, some value, let's say 20 tau. But when you are connecting the three inverters with the same loads, the D was almost 5 tau. So what we are trying to say, it is not optimal solution, though you have optimized this inverter and you are getting a least amount of delay, 20 tau. But if you could have taken two more inverters here, this could have drastically reduced the delay that we have already seen in our last examples. Yes or no?
Yes, sir.
And we also know that addition of inverter is not changing your F. It is not changing your path effort. That is why right now saying that we have optimized this particular chain when there are only two number of blocks may not be a right answer, because you know that even if you add up extra inverters, and here it doesn't matter if someone says I don't, it doesn't really matters to me whether I am getting a true form of the output or complementary form of the output, means you have the liberty to add up the inverters. You will add inverter just not for the fun. You will add the inverter only if it is assisting you in order to reduce the delay. But we should be knowing the numbers. We cannot do it hit and trial, right or not?
Yes, sir.
That is why we are making a generic statement now. What this problem statement, N1 logic blocks are already there. Ideally, there was C in here, there was C out here. But I want to check. I'm adding n minus n1 number of the extra inverter just to see what should be the optimal size of this n. Having the optimal size of n, suppose these were the two stages. Let's say I tell you, suppose I get two stages here. To n1 was 2, and finally I get n equal to 2. What does it mean? It means that my chain size was already optimal. You don't need to add any extra inverter. You are getting my point?
Yes, sir.
Yes, sir.
But if I get n equal to 6, what does it mean? N equal to 6. Existing chain is having existing chain is having two blocks, two gates. You may need to add 4 additional inverter to optimize the chain. You're getting my point? So, but right now I need to know what is this n. And in order to find out the n, which will be needing for the optimal value of the delay, you need to derivate this particular, to take a derivation of this particular equation with respect to n. Just do the differentiation. Once you able to do the differentiate it, let me know. This problem is clear to all of you. All of you need a pen and paper. Do it. So del D by del N, which you want to put as 0, has two parts, n into f to the power n by 1. So this two functions who depends upon value of n. So if you differentiate one at a time, so how much? If you differentiate n at a time, you will get f into n 1 by n. If you and you need to differentiate f to the power 1 by n one time, this portion will be 0. This portion will be P inverter. Yes or no? What is the differentiation of this one? This is the form of differentiation of a to the power x. How much you get?
A to the power x log A.
Right or not?
Yes, sir.
So the same way you apply it here. And I give you one more clue. All of you please look at here. This is the what, if you apply the log and everything, this is what you will get. Yes or no? Check.
Yes, sir.
And assume the solution of this equation give you the optimal value of n, and the optimal value of n you denote as n cap. And you assume f to the power 1 by n cap to be rho. Rho is nothing but f to the power 1 by n cap, because you can see f to the power 1 by n is repeated every time, right? And I'm saying this parameter as rho, right? So what you will get? You will get one equation. Are you getting this one? If you replace it, yes or no? If you replace f to the power 1 by n by rho, what you will get? Minus rho ln rho plus P inverter equal to 0. Or other word, if you am taking the rho equal to common, so this solution of this equation will give me the value of rho. In turns, it gives me the value of n cap, because I already know what is the f. Yes or no? Yes or no? Batao bhai. So if I tell you, usually you know that P inverter, what is the value of P inverter, parasitic delay of inverter? Approximately 1 in the conventional technologies. If it is SOI, silicon and oscillator technology, it is almost 0.6 or something. But let us assume, just to solve this equation, let's say if I say P inverter is 0, what will be the solution? What will be the value of the rho? If P inverter is 0, what will be the value of rho? Rho will be E, 2.73. Because if P inverter is 0, then in order to make the solution of this one minus ln rho need to be 0, rho should be 1, or rho should be E. Yes or no?
Yes, sir.
Right? But this is not true. Usually, if you take P inverter equal to 1, P inverter to equal to 1 plus rho into 1 minus ln rho equal to 0. If you want to solve this particular equation, it is not, you are not going to solve it from the normal computation. You have to take the numerical mean. And if you do it from the numerical mean, you will find it out the closed match comes with rho equal to 3.59. You're getting my point? For rho equal to 3.59, and you have already says that rho is f to the power 1 by n cap. So can I say n cap is nothing but log rho base f? Can I say? Take log in both the sides, you will get it this one. Yes or no? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
What we are saying, the optimal number of stages n cap comes out to be comes out to be n cap equals log 3.59 base f. Now this 3.59 number is a bit fractional. So instead of using 3.59, people use log 4 base f. They use this one. N cap optimal stages is this one. Now you may ask, sir, then why we should not take 3, why we not take 4, why we are taking it 4 right now? Very well understandable that we are taking a log in some decimal number, so I just wanted to avoid it. But is it making any significant impact in your calculation? It is not making a significant impact in your calculation. It is still that much correct as much you are getting from here. It is not going to give you erroneous output. I can prove it. So look, can you see this figure? Log rho is f. Can you see it here?
Yes, sir.
Can you also see this is the point, this is the delay, normalized delay. That is delay versus least amount of the delay. So when delay happens to be delay, least amount of the delay, can I say this value should be 1? This is this figure, delay divided by least amount of delay. When it is 1 means delay is equal to least amount of delay. Yes or no?
Yes, sir.
It happens when rho is how much? 3.59 numerically. If P inverter is 1. If P inverter is 1, this happens when rho is 3.59. Correct? Correct?
Yes, sir.
So even if you are changing, if you are roaming towards here, or you are means this is rho equal to 2.4 here, and this is rho equal to 6 somewhere here. Even if you are going here or you are going here, you can clearly see delay has a variation of only less than 20%. This is 1.2. So you can see the variation is very less than 1%, 2%. So even if I'm taking, instead of taking 3.59, if I'm taking rho equal to 4, it is not giving you any incorrect answers. Still you are very near, because you know that this n cap cannot be a fraction. Can it be a fraction, n cap? N cap is number of stages. It cannot be in fraction. Yes or no?
Yes, sir.
So let's say mathematically you are getting this answer to be 4.5. Then what should be your n cap? It should be 4 or it should be 5? If your n cap is coming 4.5 mathematically, then what should be your answer? 4 or 5?
5, sir.
Why? You are biased now? Why it should be 5?
Because the slope is
No.
Change is very less, sir.
Tell me, last
So
class,
anything can be. Anything.
when you were not knowing it, that n cap is supposed to be log 4 basis f, when you were not knowing it, what you did? You did it randomly for how many cases? For n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5. You did it for 5 cases.
yes, sir.
Yes, sir.
Now, when it is coming as 4.5, you are supposed to check for both the cases. Check it. For n cap equal to 4, you just find out the delay. For n cap equal to 5, just find out the delay. Whichever is minimum, take it. Don't fall in these traps. That if it is a decimal, if it is 4.6 or 4.7, then I am taking 5 from mathematics. Don't go like that. If it is falling in between, means you check for n cap equal to 4 and you check for n cap equal to 5. Whichever is giving you the minimum, D, you go with that. You're getting my point?
Yes, sir.
You can clearly see from rho value from 2.4 to 6 gives delay within 15% of the optimal. Even if you are using rho equal to E, some people uses ln f, and they will get some numbers. Still, they will be very near to this minimum delay. But I would advise all of you use rho equal to 4 safely. Use rho equal to 4. This is the most of the textbook they do follow. For example, the Rabbi, if you follow it, they will take rho equal to 4. Sometimes some people also change it ln f. The answers will not change because you will get some decimal value. You will get, let's say, 2.3. If you're taking rho equal to 4, you might get 2.7. You have to take a check for n equal to 2 as well as n equal to 3. For both the cases, you have to do the check. You're getting my point? Yes or no?
Yes, sir.
So what is the way to take forward now? So how exactly approach the problem, right? The first thing you will be finding out the GBH, right? That is the path effort. You know that addition of any inverter will not change the F. Hence, the second thing you should be doing is finding out optimal number of stages. Let's say your initial number of stages was 2, n value came out as a 5. It means that you need to add how many inverter?
3.
You need to add 3 inverter. After adding the 3 inverter, now you divide. Now the delay will be 5 into f to the power 1 by 5 plus p, sigma p, right? Now what you need to do, now you have, let's say your circuit was initially like this. Initially your circuit was like this, and later on you have added 3 inverters to optimize the delay, right? So this is one capacitance here, this is one capacitance here. You have verified that the number of stages is supposed to be 5. F is this one. Now what is your job? Job is now to divide efforts of each stages equally. Means G1 H1, G2 S2, G3 S3, G4 S4, G5 H5 all should be equal. And equal and how much? F to the power 1 by 2 or 1 by 5?
1 by 5.
1 by 5. Once you have done, again you do the backtracking, find out the capacitances, and once you know the capacitances, you know the WL. Was this method interesting?
Yes, sir.
Have you learned something or not?
Yes, sir.
Will you be optimize the size of the chain? If let's say in your circuit you have couple of gates or something, and someone say that you are supposed to drive a huge capacitive load, don't directly connect it with the capacitive load. I would advise check whether it is the only two stages of gates are good enough to provide the sufficient driving current. If they are not enough and you're not getting it from the method of logical effort, then what you are doing, you are basically adding extra number of inverters to drive the same load. You're getting my point? Yes or no?
Yes, sir.
Now, can you tell me, let's say you are doing the simulation in the LT Spice. You're doing the simulation in LT Spice, and you want to know, every time I'm saying the delay is GH plus P and the unit is tau, and you want to know what is the tau, then what should be your approach to find out the value of tau? That's
Delay of inverter, minimum size inverter.
I need to first open it. It got hang. Not the word. I need to whiteboard. Yeah, someone was saying something.
Delay of minimum size inverter.
Not that way. There is always. There are
Tau
always.
PHL plus. So tau PHL plus tau PLS by 2.
No, there are always. Do remember, theoretically things are okay, but when you are working with the tool, when you are working with the experiment, then you should be knowing how to measure these things experimentally. So what I will do something very good. You know that you all have heard about the Cmos ring oscillator, yes or no? Cmos ring oscillator.
Yes, sir.
Do we connect odd number of inputs, odd number of inverters, or even number of inverters?
Odd.
Odd number, right?
Odd.
Listen, right? Let's say I am having a CMOS ring oscillator and I have connected 5 identical inverters together like this. Then I know that if it is X, this is going to be X bar, this is X, this is X bar, this is X, this is X bar, right? Look, right or not? So there
Yes,
is
sir.
stable state. You can clearly see as soon as it's getting X bar, it will disturb this X, right or not? CMOS ring oscillator, this function you all must have done in the DSD or other courses. There is, you basically are exploiting, you are basically, see, now you are connecting this X bar to X, and it was the X. Now it will be forced to X bar. Again, this value will be propagated. Yes or no? What is the delay of one inverter? There is one capacitance here, one capacitance here. Can I say H is 1?
Yes.
Can I say G is 1?
Yes.
Can I say the delay is GH plus P? How much? G is 1, H is 1, P inverter, let's say I assume P inverter to be 1. Can I say the delay is 2 tau? Yes or no?
Yes, sir.
Can I say this also give you a delay of 2 tau?
Yes, sir.
Can I say this will also give you 2 tau delay? Similarly, this will also give you 2 tau. Similarly, this also give you 2 tau. Let's say you are measuring the delay at this particular point, means the effect is getting transmitted here, then it 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 is coming back. Then it is coming back. So almost until it settles, you basically looks until this effect gets settled. So almost twice a cycle you are repeating, yes or no, at the same instance. Right or not?
Yes, sir.
Almost twice a cycle you are repeating if you want to find it out what is the delay. And once you know that, if you might have seen simulated the ring oscillator in your last classes, if you know, you can easily measure the frequency of operation, and the frequency is related to 1 upon delay, right or not? Frequency is 1 upon delay. T is 1 upon delay, yes or no? In a tool, will you be able to measure the time period? All of you? You can easily measure the time period. Yes or no?
Yes, sir.
This time period indirectly gives you the delay, and this delay indirectly gives you tau. Yes or no?
Yes, sir.
So technically, if you make a setup of using a CMOS ring oscillator, what you need to do, you need to either measure the frequency, or in other words, you need to measure the time period of this oscillation. And once you put measure the timetable, once you measure the time period, you can get the information about the delay, and that information of the delay will also give you the value of tau. And that tau will be the unit, technology dependent unit, which I am saying. What should be the unit here? Is that okay? Is that okay? And also remember, have you made this ring oscillator or not in your class, like DSD? Have you made the ring oscillator, yes or no?
I mean, discussed a little. Discussed.
You have not made? Take it to the exercise in your LT Spice. Make a ring oscillator with 5 number of inverters, measure its delay, and compute the value of tau, and compute the tau logical effort. Remember, use the Spice level 3 model which are uploaded yesterday. Use the Spice level 3 models which are given to you yesterday. Remember one thing. All of you, please remember one thing, that when you make this kind of arrangement, you need to give a trigger. You need to give a trigger. Either you connect a pass transistor, because you know that there is no input. Can I see there is any input here? In this ring oscillator, can you see any input?
No,
There
sir.
is no input, right? So either you connect a pass transistor, give some input, give some input, maybe a square pulse, maybe as 1 for some period, so that things can get triggered here. Or otherwise, you replace one inverter by a NAND gate. You replace one inverter by a NAND gate. You are getting my point? You replace one inverter by a NAND gate and tie its 2 inputs to be 1 and other input to be input by the output of the chain. You are getting my point? Because you need to provide this triggering. Oscillator will oscillate unless you need to provide a trigger input. Yes or no? Then only you will get the output as something sinusoidal, right or not? Have you done it or not? Have you made any kind of oscillator so far in your courses? Analog, which you might have done in your BTech. Oscillator technically don't need any inputs, but you need to trigger it, a noise, yes or no?
Yes, sir.
For example, you can clearly see when I'm making, let's say, an inverter, ring oscillator using 3 inverters, there are no input. I know that this is X, this is X bar, this is X, this is X bar, and X bar and X cannot be equal. But you need to trigger it. You need to trigger it by some value. As soon as you trigger, then you know that, let's say you have given 1 here, it will become 0, then it will become 1, then it will become 0, then it will try to force it, make it to 0, then it will become 1, then it will become 0 here. So that way this process will go on, and it will give you a frequency with that particular waveform or something you can use always as a source of, source of a signal, or somewhere in some of the applications you can use these ring oscillators because it is giving you waveforms, right? But you need to trigger it. Triggering, either you provide through a pass transistor, you give a trigger and then cut it down. Cut it down means put this pass transistor input at for some time, for a very few microsecond, keep it 1 and then make it off. Make it off means you have given the disturbance here, now it will automatically give you the things. Or you replace one of the transistor by NAND gate, because NAND gate you can control, na? If you are keeping one input always 1, or you are keeping one input always 0, you can continue. You can change its state. Yes or no?
Yes, sir.
So NAND also, can you make the NAND as a inverter? Yes or no? First tell me. How do you make the NAND as an inverter? You could have simply made it like this. Isn't it is an inverter?
Yes, sir.
But if you want to force a particular value, just give some value to one node, and then do then basically you can have the simplest of the thing. You can have the inverter in the inverter configuration, the NAND. If you do so, you will be able to find it out the frequency of oscillation, or in other words, you will be able to find out the time period. And from this time period, you will be finding out that if, let's say, there are n number of stages, and the delay happens to be, every stage is the delay is 2 tau. So technically it happens to be 4n times tau. That is your delay, because it has to go in repeat. And this is your frequency of operation T, which is known to you. N is known to you, which is 5 in our case. Tau is basically parameter which you can compute easily. That is from the ring oscillator arrangement. That is how you can compute. Okay. So far things are all right.
Sir, it is 4 and tau because it has to oscillate twice. Is it the
It has
setting?
to reach, right? From the source, it has to reach the again at the same point, right?
Yes, sir.
So this is the method you should be using in order to measure the tau when you are doing the simulation in the SPICE. This problem already we have discussed, so there is nothing new. Yeah. There is also another way of, because I told you that solution of this equation is very complex, but you know the mathematician never leaves problem at some end, right? I know that for rho inverter equal to 1, the rho comes out to be 3.59, and I am using it as a 4. I am saying log 4 base f is are the optimal number of stages. But mathematician never leaves such kind of equation. So they derived one empirical way of one empirical equation, which are the best fit, which are the best fit, which are the best solution for this particular one, and that empirical equation is linear one. So they derived one equation, and this equation says if someone is really interested and rho inverter is not unity, if rho inverter is not unity, for example in SOI, you can clearly know that in SOI technology the rho inverter is much less. So instead of using this equation, if you use this equation, it is very close. This is the empirical relation, very easy. Yes or no? If rho inverter is 0, what is how much value you are getting? Rho is coming how much? If rho inverter is 0, what is the value of rho you are getting? 2.82. Yes or no?
Yes, sir.
Yes, sir.
Agent, it is very close to rho equal to E, 2.73 something. It's very close. Not very accurate, but agent solving this equation is much easier compared to this one. Can I say the equation which is highlighted in this yellow color, agent solving this equation is much easier because you just need to put the rho inverter value. If rho inverter is 1, how much you are getting? 0.71 plus 2.82. How much it is? Someone please tell me.
The 3.5.
3.53.
Almost very close to this 3.59 or 4, what we are telling, right? So sometimes if you encounter some technology where rho inverters are supposed to be some other value, not equal to 1 or something, then in that case, instead of solving this particular equation, rho inverter plus rho into 1 minus ln rho, you can directly follow this one. This is the empirical solution, right? A linear fit. You can clearly see this equation is linear fit y equal to mx plus c, where x is this rho inverter plus c. So you can also use this one, but in our course, rho equal to 4 will be good enough. Okay, this is only for your information. Coming to be a bit more depth of the logical effort. So far we have defined and we have used logical effort per input, but people also do define the logical effort of a bundle. I will give you a couple of examples, and they also define the total logical effort, the logical effort of when all the inputs are taken together. The input group contains all the input signal of the logic gates. I will be telling you. Okay. I am also dealing with some asymmetric logic gate. I also told you, I gave you, I think, this example already. For example, you have A plus BC whole bar. This is the example. You can clearly see the, if I do remember that my standard inverter happens to be, what is the sizing? 2 here, 1 here, VDD here, ground, and this is the output, and this is the input. If I say this is the standard inverter, and I know that capacitance here happens to be 3C, right? So you can see input GA, logical effort with respect to input A is how much? What is the net capacitance for the input A? 6C divided by 3C, how much? 2. And this is also equal to GB, yes or no? A and B, both inputs are having the logical effort, how much? 2, yes or no? Yes or no? Am I audible?
Yes, sir.
Is it clear? GA and GB both are equal to 2. While, what is the GC? Logical effort of C?
So 5 by 3.
5 by 3. It is not equal to G and GBC, right? So you know that with per input, you can clearly see if there is a asymmetric logic gate or something. You are visualizing this as a 1 gate unit. You can clearly see logical effort may vary from input to input, right? But your interest, if I say the critical path is from A, then you are concerned about GA. If I say critical path is from C, they are concerned from the point of the C. Okay. Similarly, there are Xor Gate. In Xor Gate, you know that A and B are there, but you also know that A bar and B bar are also generated using, they are generated using what? From A only, right?
Two in
From A only. So gamma is here, the mu raised to mu p is the gamma raised to 1. You may be afraid what is the gamma. Gamma is gamma raised to 1. It's general. For example, in our case, the similar case, I can say this is 4, this is 4, this is 4, this is 4. Isn't it is equivalent to a standard inverter? Yes, it is equivalent to inverter, standard inverter. So you can clearly see A is also getting by the A bar generated, like A bar is also getting generated by A. So instead of defining only for one input, you basically bundle all these input together. So what happens to net capacitance? Net capacitance happens to be 4C, 2C, 4C, 2C. How much? 12C. 6C plus 6. 12C divided by 3C. The logical effort comes out to be 4 of GA and GB. So right now you are taking as a bundle A and A bar. Why? Because you know the A and A bar, it's not you are putting the A bar separately. You're generating the A bar from the A itself. Yes or no? Yes or no? You're getting my point, all of you?
Yes, sir.
You also know that you will be generating it through the inverter. It is not making a difference because the inverter has a logical effort of
1.
yeah. Now coming to how to calculate the parasitic delay, I don't need to go to this theory because already you know RC delay model. So can you tell me what is the parasitic delay of this particular one? I told you for parasitic delay, you do compare with the standard inverter delay when it is not driving any load. You know that net capacitance here is 3C, correct or not? Net capacitance here is 3C. Yes or no? For an inverter. 2C because of this one, 1C because of this one, 3C you are getting it here. Yes or no?
Yes, sir.
Yes, sir.
So if I can say that my inverter will take either 3 RC for charging time or 3 RC for discharging time. Now someone asked me what is the parasitic delay of this gate with respect to this inverter. I will first find out what is the capacitance here. And from RC delay model, I know that 2C because of this one, 2C because of this one, 2C because of this one, this was 6C. So can I say the parasitic delay here will be 6 RC divided by 3 RC? That happens to be twice of P inverter. Yes or no?
Yes, sir.
What is the parasitic delay here? Can you tell me if there is one gate like this, what is the net capacitance at this node? Can you tell me what is the net capacitance? Can I say from pull down network, this is 2C plus C. From pull up network, how much?
11C.
4C plus 4C, how much? 11C, right or not?
Yes, sir.
11C divided by 3C. 11 by 3 P inverter. Correct, yes or no?
Yes, sir.
But can I also implement this same circuit by using this? See, the function here is how? What is the function? AB plus C whole bar. AB plus C whole bar. Can I say this is AB plus C whole bar?
Yes, sir.
Yes, sir.
What is the parasitic capacitance I'm getting? 11 by 3 P inverter. Can I say the same implementation of this circuit can also be done like this? Is it still AB plus C whole bar? There are two different topology now. I think this one is the same and this one is this one. Are both same or not?
Yes, sir.
So what is the parasitic delay here? Here you are getting 2 plus 1. That's 3 plus 4, 7 plus 4, 11 by 3 P inverter. And here 4 plus 2 plus 1. That is?
7 by 3 P node.
So can I say this one is giving you the less parasitic delay compared to this one? Though logic function is same.
Yes, sir.
Yes, sir.
So sometimes, as I already I'm telling to you from a lot of time, the parasitic delay, this particular component, the way you place your transistor, if you are providing junction sharing, you might have seen in RC delay model, right? You can always decrease this delay. Parasitic delay, the component GS plus P part. Okay. Well, with this, we are ending the lectures on logical effort. and I think we have given enough time this time for the logical effort. It is not that we have paced it up. I have given you enough